There we go. So this is the second demo of today, and I threw something on the agenda, and I'm the only one who threw something on the agenda. So um, I'll just go ahead and present this thing to you, my audience. um,
Sounds good.
yeah, it's actually something we talked about, or it's something you're familiar with, I think already. Um, So it's about a bottleneck I discovered in gRPC, the way we used in Italy. And um, so I I got thinking about this because of the back objects cache. And when we tried to turn it on, which is a change you made, at some point, no, wait, that did not get reverted. But then I tried to bypass the preclone script for GitLab or GitLab, and that got reverted because the apdex of Falcon Area 1 started going down. And then I tried to understand what is wrong here. And at the end of that investigation, I suspected that we were hitting a bottleneck in gRPC, but I couldn't really prove that. So I just had to close it and we wrapped up the epic. But I kept thinking, I would really like to know if this is true or not. So then what I ended up doing, one reason why, so the graph just showed like Italy was doing a lot of stuff. I think that's one of them. Okay, maybe I should just go through the reasons. What I should try to stick with my story. So I have a bit of a story. Let me share my screen. So there's an issue where I try to explain this. So one thing is that we never had, this is the Git process activity graph, and we never had Gitly in here, and we only added it at the end of the pack objects cache project. And then I started noticing that Gitly is like the top thing most of the time, Gitly itself. And I mean, we always were tracking Gitly CPU utilization, but it was in a different metric, and we never had the two things in the same graph. So then it doesn't jump out at you that much. Now, the other thing I noticed while working on the project was that the Gitly allocates a lot of memory when it's serving traffic, and it all happens in the functions that are responsible for transferring Git HTTP data. And so in this profile, like the top line, it's hard to see, but it says 40 gigabytes. And it basically looks like, and if you click these traces, it's gRPC stuff. So it looks like gRPC is allocating memory proportional to the amount of bytes that we're transferring. And if you're just copying data, that's not good, because that should be a constant time allocation per request, not ON in the number of bytes you're proxying, right? That I found that suspicious. So I was, yeah, just because of the allocations, I thought something fishy is going on here, and I wonder if we make this just constant in allocations and not linear in the requests or in the response size, what would that give us? Yeah, and then the other
I've,
thing I noted. Go ahead.
yeah, I've got some interesting, possibly related data to share, but I don't want to interrupt your story. So
Okay.
let me put a mental bookmark there, and we'll come back
Yeah.
to it.
So the other thing, besides the allocations, which in themselves are fishy, and in retrospect they're super fishy, but we'll get to that. I also noticed, looking at CPU utilization, that if you look at write activity, these are the threads. So this is the CPU time spent doing writes, and these are actual syscalls. But all this is stuff where we're putting messages on a queue inside the gRPC runtime to deliver them to the threads that are doing the writes. So we're actually spending more time telling gRPC to send something across the network for us than it takes to send it across the network. And that also points at an inefficiency.
And this is specifically CPU time we're talking about here.
Yeah, this is a CPU profile.
Not wall clock. Yeah.
Yeah. So I thought, how can I test this? And then I realized I can just try. I only care about Git HTTP, so I can just try to build a toy version of Gitly and a toy version of Workhorse that only knows how to serve a Git HTTP fetch request, but build it on top of TCP sockets and nothing else, and benchmark that. And that it turns out that that is insanely faster. and that's sort of the story. And I have a table here at the bottom where I set this up on a virtual machine with the same machine type we use for GitLab servers. So a C2 standard 30 as the GitLab server, and then I had a client machine fetching the data. And I have a load generator where I was doing 30 clones in parallel of the same repo. And that load generator will saturate the GitLab server one way or another. And the interesting thing is how it saturates. And what you see is that if you don't have the cache, then it saturates at 920 megabytes per second on the network, and your system load goes to 148, 83% CPU utilization. If you add the back objects cache, you get more throughput, but you get the same system load, you get slightly lower CPU utilization, but you're basically still CPU saturated. Now, Rpc Test is this thing I built that just uses a TCP socket, and you get twice as much throughput, and you get almost 100% CPU utilization, so it's still being saturated. The craziest thing is that the moment I turn on the cache with that thing, we hit 4,000, nearly 4,000 megabytes per second, which is the hard limit that GCP puts on the network, and we're no longer under CPU saturation. So we can break through this wall of 1 gigabyte per second to the maximum the network offers, and we saturate on the network before we saturate on the CPU. So we just completely changed the performance profile of the whole thing. So I was kind of blown away when I realized that that was possible. And if you have no immediate questions, I can show you some flame graphs that make it a bit clearer what's going on.
Yeah, I was going to say this looks like spectacular results, and that, of course, as a scientist, that always kind of evokes questioning the results. I would love to see some profiles, some CPU profiles in particular.
Yep. So this is a profile. Let me just. So this is slightly annoying. I need to download it and open it so we can click around.
Yeah.
This is with the cache off. So we do have the overhead of the cache plumbing, but 0%.
And it looks like this is Giddily, not your.
Yeah, exactly.
What was the toy thing called?
Rpc Test.
Rpc Test. Okay.
Great. Yeah. So this is Giddily, and this is the case where we're saturating at 920 megabytes. Okay. And load is about 1.4, and you can see we're not at 100% CPU because you have the swapper down here.
Yes.
Right.
Right. And this is just for clarity. This looks like a perf profile, and I'm guessing your sampling rate was like 99 or
99 hertz across all CPUs, 30 seconds.
Okay. Yeah. Okay, great.
Which is sort of my go-to. I have a script that does that I can just point at a random server, and it SSHs in it. It does that.
Yeah.
So yeah, CPU profile all cores. So it's not saturating all the cores.
Yes.
Giddily is the biggest workload, followed by Giddily hooks, which is this in-between component, which is we use for the caching, and it acts as a gRPC client. And then this is a collection of Git processes that is serving Git response data. So if you look at Giddily hooks, one thing that's interesting here is that you see lots of garbage collection. This is a garbage collection function. Without knowing in detail what the Go runtime does, this is garbage collection, obviously.
Yes.
This is garbage collection.
Yes.
And well, over here you see it's actually reading from a network connection.
Network file descriptor.
Yeah. So that is getting data from Giddily, but so that's this little tower. But for instance, this is just communicating with the flow control mechanism in gRPC Go.
Oh, this is the scheduler. Okay.
Yeah, so this is gRPC Go's scheduler, right? It has its own scheduling for I/O, even though this thing has only one connection that it has to work on because it's a single process. More GC, and then also here, like here you have kernel stuff, right? It's doing writes.
Those Giddily hook are those short-lived processes?
Yeah.
Okay, I assumed so because
Yeah, they're one per clone.
Okay.
So the main thing is you see quite a lot of garbage collection on these one per clone processes. And if you look at Giddily, then, well, that's the same picture I showed you before, but upside down. So here you have syscalls where it's doing reads. That's the process generating data.
That's reading from a pipe, it looks like.
Yeah. Exactly, pipe read. These are the writes that go into the gRPC message queue. It's submitting So this is not I/O. This is just submitting to a message queue in the process.
Okay.
And this is the Go routine loopy writer you can see at the bottom that sits at the other end of the message queue and that actually does I/O.
Okay.
So here you see network writes, socket writes.
Yes. Great.
But
Okay.
only this narrow tower is socket writes, right?
Yes.
And
Right.
it's dominated by other stuff. So that's what things look like with 0 cache hit rate. Next, I should show you what it looks like with 100% cache hit rate, but still using Gitly.
Makes sense. Should have a lot less in time spent in Git, I'm sure.
Yeah, let's get that one. So we're still not at 100% CPU. And that's also what I saw, like it was something like 77%.
Yes.
Git is much smaller here on the left, but Gitly hooks and Gitly are still pretty big. And if you would drill down into what they're doing the same stuff.
Okay.
Do you want to see more detail on that, or do you?
No, that's fine. Yeah. Keep going.
Okay. So next, I can show you RPC test without cache.
Okay.
So this one was load 189, and it was 100% CPU utilization, and that also is borne out in the profile picture because the swapper is all the way over here on the right, and it's tiny.
Yes. Yes. Okay.
This is Git processes.
Yes, that makes sense. So we're driving. Okay, so that makes sense. So because we're driving more Git processes because we've got higher throughput.
Yeah, exactly.
Which is why Git's taking more CPU. Okay.
Yeah, otherwise Git is just stalling because it cannot feed its data to Gitly because Gitly is not accepting its data fast
consuming
enough.
It fast enough.
Yeah.
Yeah. Great.
So this is the equivalent of Gitly hooks, and this is the equivalent of Gitly.
Gitly. Yeah.
So if we look at Gitly hooks, then this is writes on, these are pipe writes, Futex wake.
There's if you don't mind, let me pause you for a second just for some basic background. I've spent a decent amount of time with Gitly and in kernel code, but I haven't spent any real time with Gitly hooks. That's a separate process that gets forked for a short amount of time, and it effectively acts as a pipe between child processes in Gitly, or what's the...
So normally every fetch request corresponds to a Git upload back process.
Yes.
Right? And Git upload back can do several things, but the most expensive thing is sending back file data. And that is farmed out to another sub-process, which is called back objects.
Back objects.
Yeah. And there's a hook mechanism in Git where it will run a different executable instead of back objects.
Oh, okay.
And that's Gitly hooks. So every request creates an upload back. Every upload back creates a Gitly hooks. Gitly hooks goes in with the Unix socket back to Gitly. And then Gitly can either fetch the data from a file, if it's cache, if it's a cache hit, or it runs back objects the way upload back wanted to run it in the first place.
Yes, makes sense. Okay, great.
So it's
and we spawn this hooks process for every call, right? Was this in place before for every upload pack will always invoke the hook regardless of configuration?
Yes. So that is a design choice we had to make when working on the cache, and
that makes sense.
It appeared to me, but I didn't understand this well enough at the time. It appeared to me that it did not add noticeable overhead, and in the case where the cache is active, it reduces overhead because you have fewer Git processes, back objects processes. But
yes,
it's effectively a Gitly client, right? Because it makes a Gitly call and it's copying data from the Unix socket to standard output, and so it does the same job as Workhorse and GitLab shell, except it runs on the Gitly server.
Yes, yeah, I've seen that the post upload pack and SSH upload pack nowadays, now that we've got the caching enabled, have a similar number of another gRPC call whose name I'm forgetting.
Back objects hook.
Thank you. Yes, but yeah, I was going to say it clearly relates to this.
Yeah,
it's the other half of the action,
exactly. It's the thing that Gitly hooks calls. Gitly hooks also
sense.
has other jobs. It was created to do other jobs, and it already existed. And added
Okay.
another subcommand to it. But
That was my next question. Yeah. What else
yeah,
do we use Gitly hooks for? Okay.
well, as you can guess, maybe Git likes hook executables as a plugin mechanism, and
Yes.
it's part of Git push. During Git push, there are hooks before and after the references get updated, and that's
Yes.
how we trigger CI pipelines, how we know a user pushed,
Okay.
how we implement protected branches. All that stuff is built on
Yeah.
hooks, and those
Okay.
go through Gitly hooks as well. And then it also makes an internal gRPC call, except those are not a lot of bytes. Those are relatively small.
Yes. Okay. Fantastic. That makes sense. Thank you for sorry for the
Yeah.
tangent,
No,
but
no, no,
that
no.
was super helpful.
Great. Thanks for asking. So yeah, Gitly hooks already existed, but it was not part of the chain for Git fetch.
Mhm.
I made that change because of the cache.
Mhm.
And yeah, so we see it being busy.
Yes, makes sense.
And what we see here is that the replacement based on sockets is spending most of its time doing writes,
Yes.
futex waits,
It's
socket
all
reads.
it's all copy buffer. That's
Yeah,
fantastic.
exactly. It's all exactly. That's what it's supposed to be.
Yeah, that's his job.
Yes.
That's wonderful.
Yay. uh, and here's the Gitly replacement. And again,
Okay.
it's all copy buffer.
Okay, cool.
And
And
yeah,
that's by design. That's trying to
yeah,
maximize the
yeah,
throughput.
exactly. The idea is just we should only be doing copy buffer and we should not be allocating anything. And what
Mhm.
if we only had to do copy buffer? That was sort of how fast can
Mhm.
we go if we can somehow optimize things that we only have to do that on this code path? That's what I
Makes
was trying to
sense.
figure out.
Cool.
So that's without cache. So it's a 0% cache hit rate effectively.
Okay. Would you zoom in on that tower one more time? The
Which
RPC
one?
tower.
Yeah,
The Gitly. Yeah. Perfect. I just wanted to, yeah, take another peek. So we've got
yeah.
about maybe 30% in pipe read. What's the middle tower?
That
Scheduler.
is polling. The Go
Oh, okay.
runtime uses async IO
Yes.
and the syscall here is epoll.
Okay. That
Yeah,
makes sense.
it's yeah, that's how Go makes IO efficient. Like it all the Go routines that want to do IO register with the polling subsystem, and then one thing is doing the polling and waking up Go routines when they have something ready for them.
Makes sense. Okay.
Yeah,
And then the left-hand tower is socket
sock
right.
right.
Great, 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 great.
Yeah,
Fantastic. Okay, thanks.
yeah. So this was like where we hit, like I said, swappers almost nowhere. So it's 100% CPU. We're actually completely
Yes.
CPU saturating the Gitly server.
Yes. That's
And this was,
that's cool.
yeah, and
That's a reasonable bottleneck.
yeah. And the repo we're using here is the handbook, which is a very large repo. So
Oh, okay.
a lot of the time, because I did two sets of tests. I also tested it with
Yes.
GitLab or GitLab, which is about 1.5 gigs, and the handbook is like 5 gigs. And
Yeah.
you see the numbers shift a little bit because
Yeah.
we have more requests in the case of the GitLab or GitLab in a 30-second window than we do with this one.
Okay.
But yeah, so that's this story. And then the really cool one was, of course, where we have the cache hits. So let me get that one.
Mm-hmm. Yeah,
So
because the
swapper,
get pack objects process is not cheap,
wait,
especially for a
I'm in the
non-trivial.
wrong flame graph now.
Okay.
Sorry, this one, this is the right one.
Ah, RPC test with cache. Great.
Yeah, swapper, 52% swapper.
That is unbelievably beautiful.
Yeah. There's one little detail that I want to show you that
Okay.
is really cool.
Yeah.
The Go runtime, in some cases, is smart enough to use send file. The send file, so the send file system call allows you to copy data from a file into a network socket
Descriptor.
without having
Yeah.
to go through user space, which is really nice. So what you
Yeah.
see here is that all the hook serving traffic is going into send file. Wait, let me just blow this up.
Yeah.
Do send file. So this is it's not even in copy buffer. It is just doing send file because one end
Yeah.
of the connection. Even I mean, in the current situation, we have a socket and we have a file, but because there's these layers of abstraction in between, the Go
Yes.
runtime can see that that's what's there, and it cannot
Yeah.
use this syscall.
Yeah.
But because we peel these layers away, this optimization can kick in, which is just a nice gift. And there's another nice gift that I didn't even do here, but if you have if you think of upload pack, right? It has a standard out pipe,
Mhm.
and you have a socket. You could also dub the socket and make that the standard out of upload pack, and then upload
Mhm.
pack's writes go straight to the kernel and never go through Gitly. That actually
Mm.
works, and it's like 10
Okay.
lines of code. And then the Gitly CPU just goes to almost nothing because you're doing constant time Gitly work. It's just a send file one send file per request, and it spawns upload back, and upload back. Actually, I have a no, I don't have a profile for this, but when that happens, it's really cool.
Yeah,
Uh,
I'm kind of surprised that that's possible.
yeah, see, here it says pipe writes, so there it will
Yeah.
then says socket writes
Yeah.
because it's just a file descriptor.
Yeah.
You're actually allowed to do that, which is just
Okay. So we're delegating the file descriptor to Git upload pack.
we could, but of course the downside is that you cannot do user space crypto anymore if you do that. So then you
Yeah, that's true.
it's if you have the socket object, it's very easy to write the code that automatically does the upgrade. But if you want to do TLS, then you're back in
Right.
user space. So I
Yeah.
figured I'm not going to put this in here because then it gets
Yeah.
too exciting, but I cannot shut my mouth about it either because it's just cool that it's there.
It's yeah, no, that's awesome that it's there. That's fantastic.
Yeah, thanks. So yeah, this is mostly copy buffer, a little bit of send file, and then
Okay.
the hook executable is still copy buffer like it was
Okay.
before.
Okay.
So, and at this point, we're well, obviously we're not saturating the CPUs, but the load factor is also like way below 1. I don't know what I said it was, 0.6 or something.
Yeah, it
Yeah,
looks like about half. Yeah.
0.57.
Cool.
And yeah, I had to look it up, but the limit, apparently the limit on the VM is 32 gigabits per second. So if you divide that by 8, that's 4 gigabytes per second,
Mhm.
and we're almost at that limit.
Yeah. Yeah, and it's an approximate limit too. So I would be astonished if that
Well,
wasn't kicking in here. It's proportional
actually,
to the. Oh, go ahead.
if I do that thing where I dub the file descriptor and sorry, dub
Yeah.
the socket and give it to upload back, then you really hit 4,000. I have like if I go back in
Yeah.
my I have graphs where it hits 4,000. Okay, I'm not gonna. I could pull up
Sure.
Prometheus graphs where it hits 4,000.
Yeah. 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 Yeah.
um, it just didn't in this particular configuration. And the
Mhm.
other thing that I wanted to highlight here is that in either of the Gitly situations, if you look at a memory profile, then you see that in 30 seconds, it allocates 115 gigabytes of memory. And
Mhm.
this all has to do with protobuf marshalling and stuff that happens in the this async IO queue that is part of gRPC.
Yeah.
And so that's 100 gigabytes. And then if we look at something like Rpc test with cache, sorry, wrong, scroll down, it's 5 megabytes. So I was saying this should be constant in the amount of
Yeah.
bytes, not number of bytes, and it is. It's like to go from 100 gigabytes to 5 megabytes
Yeah.
allocations is a little.
Yes. No, that
uh,
makes sense. Yeah. Yeah. I guess I can rationalize why we'd have a really high churn on the heap when we're doing multiple layers of short-lived
yeah,
IO.
yeah. I think that it's just I don't very deeply understand how gRPC works, but I think one of the main things they try to do is connection multiplexing. Well, it's
Mm.
built on HTTP2, which also has on one of its main features connection multiplexing and flow control.
Yes.
So all things that go across the connection are messages, and these get put in a queue, and then there is this central thing that owns the connection that looks at which things want to go on that one connection, and it feeds off their queues, and it implements a quota and things like that. So that's sort of what they built. And the way it works is that, yeah, you have the submitting part of the queue, and there they run protobuf itself is not helping either. They serialize byte slices into protobuf messages, put a length prefix on that, chop that into 16 kilobyte HTTP2 frames, maybe do a couple of inefficient things in the meantime where they allocate some things twice, and it goes on this queue, and then it needs to go out the queue. So I think it's a fundamental thing about this multiplexing async IO design that the library forces on you, plus that, in some cases, like send files never going to happen this way, right? If you have that stuff in between.
Yeah, that makes sense.
So how does this tie in with what you wanted to say about memory?
Yeah, so on a hold the screen share for just a second. The yes, thank you. Slack crashed while you were chatting. Yes, so I spent more time than I expected to digging into this. Several customers, several self-managed customers reported that they have large. You've already got all of the context, so I'm just kind of for anyone else watching the recording, summarizing it. So this, in brief, we have multiple large customers running non-trivialized Giddily nodes where they have observed abrupt spikes in memory usage by Giddily that do not go away after the surge in workload. And we're pretty confident that from bits of diagnostic data that those customers were able to send us, we're pretty confident that what's going on here is there's it doesn't matter what the event is, but there's an event that causes.
I have a hunch what the event is, but go on.
I suspect that there are several ways to trigger this, which is kind of why I'm glossing over the event. And I know that you found one that was very convincing, and I bet that
because that one is doing allocations in a loop, and it's not constrained by having sent things back to the client. So if that runs out of control fast enough, I can imagine that the runtime responds by just making very large allocations.
Yes.
Yeah.
So once the runtime allocates, what we're kind of analyzing here is the interactions between two discrete memory management frameworks, one of them in the Go runtime and the other in the Linux kernel.
Yeah.
So Go runtime allocates a large chunk of virtual memory, which we're going to call a map. And most of that is not actually allocated to physical pages most of the time, but those pages can be allocated on demand when via a page vault.
Yeah.
And what we think is going on is the Giddily memory, the Go runtime's memory management framework has two options for. I'm going to wrap this up because I know you already know this.
I think you talked about this last week too, but I wasn't in that call, so don't wrap it up too fast.
Okay. Well, we know more now than we did last week.
Okay.
So that, and the thing, I'll zoom in on this flame graph in just a second. By the way, if anyone's interested, this is the issue ID 3567 in the Giddily repo, and there's a short status summary at the top of the issue that's up to date as of yesterday. But the short version is the Go runtime's memory management has two options for how it notifies the kernel. Hey kernel, this chunk of memory, it's semantically safe for you to reclaim it if you want to. And that notification mechanism is using madvise, and there are two bits of advice. The two mechanisms are madvise free and madvise don't need. Madvise don't need is what historically the Go runtime used until a couple of years ago. It switched to madvise free because of some perceived efficiency improvements. And in the latest release of Go 1.16, they're switching back to don't need as default. And that's probably going to be better behavior for us. And there's a caveat though. According to the documentation for the madvise syscall, the behavior of madvise free is very different on systems that have swap enabled versus have no swap. And all of our Giddily hosts have no swap. And I think that's why we're not observing the behavior that these customers are reporting.
Yeah.
The behavior, and I have not empirically tested this, but I think the kernel documentation is reasonably trustworthy with regard to how it handles these syscalls. So I'm taking it on faith right now that it's correct in saying that when madvise is issued with the madvise free advice, if the host is swapless, that memory gets immediately reaped, which is pretty similar, but not exactly the same as what happens with don't need. If, in contrast, on a system that does have swap enabled, which we think these customers do that are experiencing this problem, then madvise free is very, very lazy in reclaiming memory. The kernel has a pretty abstract mechanism for computing a perceived amount of memory, numerical value for memory pressure. And that has to exceed a certain threshold for the kernel to even bother reclaiming that memory. And I suspect that because we know Giddily benefits enormously from the file system cache, and the file system cache is kind of the first victim for relieving memory pressure, it's pretty likely, in my opinion, that these customers are experiencing a performance regression because Giddily spikes its memory usage, which steals memory from the file system
cache. Page cache, yeah.
And then it never gets reclaimed by the kernel because of this mechanism. And if we tell the Go runtime to switch to this mechanism, it's more likely to release that memory and hence make it more available to the file system cache.
That's one thing we saw. Well, that you probably already knew, but that I sort of suspected, but that became really clear to me when working on the cache, is that the page cache really works well with Git, and it's not surprising because Git was designed to work well on Linux.
Yes,
designed for Linux.
Right,
so,
right.
It's
in more ways than one.
Yeah, exactly. But if you have something that is just eating into the space for the page cache, then you're going to end up doing actual block IO, which is not what you want. Yeah.
Yes, exactly. Okay, so onto the other bits that I wanted to share. So I wanted to try to quantify. So the proposal that we've kind of reached here is there's
they can set that via Go debug.
Yes, exactly. Yeah. So we haven't applied this to our hosts yet, but I think we probably should, and I think a lot of folks are in agreement that we should do that. And I'm
just so we know ahead of time what's going to happen, because it will happen eventually anyway when we reach Go 116. But then we can wrap this up and we can say, okay, this works, hopefully.
Yes, exactly.
Yeah.
So in our current state, I tried a few tactics for trying to what's the best way to summarize this? So let me I'm sorry, let me take another couple minutes for one more piece of background.
It's okay.
Okay. So this is one last bit about the interaction between the Go memory management and the kernel memory management. When the Go runtime issues that madvise syscall to say this range of pages are you can reclaim if you want to, that is effectively saying, I know that you've allocated physical pages for this portion of my map. If you want to reclaim them, you can. I will probably use them again in the future, but feel free to reap them at your discretion right now. And the behavior, the interesting behavior here is, if the process in this context, the Go runtime, touches this is the semantics of the madvise syscall. So this is Linux behavior. If the process that has issued that madvise touches that page again before the kernel reaps it, then the mark that says that this page can't be reaped gets implicitly removed.
Yeah, of course. But that's what you would expect. Yeah.
Yes, exactly. And so the rationale for using this kind of asynchronous reaping behavior is that the Go runtime can be fairly aggressive in marking pages that it thinks it won't need again. And if it ends up wanting to use those pages again, it doesn't have to worry about whether they're there or not. The kernel will allocate a page if there isn't.
Right, because it could also shrink the map or something like that. But it doesn't shrink the map. It just says I don't need most of it. But
yes,
it could just barge in and claim an insane chunk of memory.
Yes.
Yeah.
Yes. Exactly. And so the rationale for making this a lazy reclaim is that if that page that got marked as reclaimable ends up getting used before it gets reaped, then that saves the kernel the bother of A, the reaping, and B, the reallocation of a user page.
It just doesn't have to update its data structures. They just set a bit somewhere on the page and move on. Yeah.
Exactly. And so I figured that because the mechanism for provisioning a page, that has been reaped, is to do a page fault, specifically a user space page fault, that we could trace page fault events and try to identify when those page fault events correlate to the Go runtime trying to access a page in its map. And that turns out to be really difficult.
Soft page faults.
Yeah. So this note here, I'll link this in the meeting doc. But this note here kind of walks through that experiment, and I thought it was interesting enough to share. The short version of it is that I found a trace point that lets me excludes most of the syscalls like read and write and execde and pipe read and things like that we don't care about. The only page faults that we want are ones that involve the private anonymous memory that's been allocated to the process, and the process is directly accessing it.
So you're saying those other syscalls also cause page faults?
Yes. There's a lot of ways to cause page faults. So we can't just look at the system at the overall page fault rates.
Okay. Thanks. Yeah, go on.
Yeah. So looking at and page faults happen really, really often. So I also needed to find a trace point that would support kind of subsampling. So I got this one to give me a 1% sample. This is the first of the two flame graphs I wanted to show. So this is effectively saying 1 out of every 100 page faults that are initiated from user space, go ahead and capture a stack trace, a user space and kernel, and and so you can see a lot of Git processes are doing
which are all one-offs, so they're going to be constantly needing to do this again.
Yes, I'm going to just zoom in on a couple of these so we can see more detail. So this is for example, this looks like a Git diff, and it's reading a pack file entry.
Yeah.
That sure makes a lot of sense. So it's doing a mem copy of a page that's presumably from the frosting cache into memory, into a private memory allocation.
Yeah, and the thing is that when it comes to reading the pack files, if something is in the file system cache, it would still be a soft page fault, right? If the process has never looked at it yet. Yeah,
that's right.
Because I was thinking Git also has to allocate memory itself for decompressing things, because it's not just enough to load the data from disk. It's compressed, so it needs memory on top of that. But this could just be the IO that we're seeing here.
Yeah, that's exactly right. And we can see here is Git calling malloc, which
that's where it would put its temporary structures. Yeah.
Exactly. So just kind of scrolling for folks who don't spend a lot of time with flame graphs, which I know Jakob does. These are sorted alphabetically from left to right, each layer of the frames. And so we're looking for the Gitly process, and I'm going to move and you can see it's not obvious. So I'm going to move my mouse very slowly right here, and you can see there's Gitly -git go,
which is again a one-off process.
Yeah. Here's Gitly hooks. Scrolling, and over here, that's Gitly. That's the whole thing.
Yeah.
149 frames. So this is 149 frames out of this is 149 samples out of about 20,000 samples. So this is a vanishingly small amount of times that Gitly itself is doing page faults of this variety. And the second flame graph.
When and where did you capture this?
This was on, did I note that here? I don't think I did. This was on one of the production Gitly nodes.
Right, so this is production traffic.
It's production traffic. Yeah. It's 60 seconds of production. I try to name the files with clues about this. So this is a software type of perf event called page faults. It's capturing 1 in 100 of those events, and the duration of the capture was 60 seconds, and it was on one of the production Gitly nodes. I think it was file 42.
Yeah. I guess that this shows that the Go memory allocator both our workload is probably very constant, and the Go memory allocator is doing a good job of not of keeping things around that it needs, or not releasing too many things.
I think so, yes.
Yeah.
And just for reference, the second flame graph I attached here is just extracting the 149 frames that we zoomed into here, just so it's easier to see them. But I think the kind of the first most important message is that there were very, very few of these events, which suggests that the Go runtime is doing a pretty good job.
Yeah, but also
in its current configuration.
Look where these are.
That's the second thing I wanted you to see.
Yeah, so that is smart HTTP post upload back. So that's Git's HTTP proto marshalling, and the one on the left is back objects hook, which is the bulk of the data that flows through post upload back throws through back objects hook first, and then back out through that sub process, Gitly hooks, and then back in, and then out the door again. So yeah, that makes sense.
Yep. So yeah, this is more of the gRPC marshalling you were talking about. There are, I guess, the other interesting bit that one of the things that I was looking for here is an efficient way to quantify how often we end up having page faults in when trying to allocate memory within the Go runtime. So we would expect that that it's very, very frequent to have to do allocations within the Go runtime that don't cause page faults. And I figured that one of the useful tricks for us to kind of quantify the impact of either the new Go version or toggling this M-advise mode would be to count the ratio of allocation events versus page faults that derive from those allocation events. This doesn't get all the way there, but it gets kind of close.
Have you looked at the Go runtime pprof?
I haven't spent a lot of time with it
because Go it emits numbers, well, some numbers, so it could be that it has its own metrics for that. What the thing you want?
Yeah, so I can't speak I can't speak well to that because I haven't used it enough to be confident in my interpretations. But my impression is that we're talking about heap profiling here. My impression is that the Go's internal heap profiler biases towards sampling. My impression is that it biases towards sampling large allocations over small allocations, and I don't know how much control we have over that. And
can I show you something?
Sure. There's one other thing I want to show here.
Oh, yeah. So I'll show when you're done. I'll show you. You want to finish your thing?
Yeah.
Yeah.
Sure. It's very quick.
Let's do that.
Okay. In the spirit of finding ways to instrument this, I wanted to highlight that that about 44% of these were doing sorry, these are page faults. So this is this portion of the stack is there are two common call paths near the tops of these stacks that actually did result in page faults. One of them is when the runtime is trying to effectively add a new span to the M cache, and to do so for whatever the size class that's needed that needs a refill, it will call mcentral grow to allocate a new set of spans, and that it's perfectly reasonable to expect that to sometimes do a page fault when it's doing that by touching a portion of the map that has not yet been physically allocated to the page.
Yeah, and also Go memory allocations are always zeroed, so it could be that the act of zeroing is what causes the page fault, and that's why we would see memclear at the top.
It's always going to do it always does the zeroing, and that's Yeah,
that's writing into the mapping. So it could be that is what causes the page fault.
Oh, sure. Yeah, I guess my point is that if the page has already been allocated from the kernel, we wouldn't have seen that as a page.
Exactly. Yeah.
Mm-hmm. And the other interesting stack is this one right next to it, the runtime.large alloc. So anything that's, I think the size classes end at like 32 kilobytes. So any allocation that's larger than 32K ends up getting allocated directly with this large alloc call. And so that, just exactly like you just said, that also returns zeroed pages, which is why it traverses this. And it's natural to expect that to also occasionally induce page faults when it's touching a portion of the map that don't currently have a physical page allocated. So where we're leading up to with this is, I think maybe these instrumenting these two functions. I haven't written this yet, but I think that probably I could instrument these two functions in the Go runtime, and either a kprobe or a trace point for page faults, and only track the page faults where
that happen under that
yes,
those functions
under that call path, exactly. So that would be effectively set a bit here for this particular task ID, and then if there's a page fault event, that
or just memclear no heap pointers, right? Because that's common to both of them.
Yeah, I don't know if that's called in other places, but maybe so.
Well, it doesn't matter if it's called, but if it's called and it does a page fault, then it's clearing something that wasn't there before, right?
Yeah, I like that. Let's go with that.
It doesn't really matter if it's one or two, but it could be one from the sound of it.
Well, this is a minor point, but yeah, that's fantastic. This is a minor point, but the spelling of this symbol turns out to be really obnoxious because it's got a parenthesis and an asterisk, and
good luck escaping that.
Escaping that is hard. Yeah, I worked out a way to do it, but it's obnoxious. So I'll stop sharing now, and you can.
Well, another argument in favor of memclear no heap pointers then.
Yeah, exactly. I'm going to make a note of that right now.
So what I wanted to show you, let me share it back, is that, oh, come on, why am I not typing in the right box?
So we were talking about heap profiling.
Yeah, mem stats. Yeah, this whole namespace. So I think this has things like heap sys bytes. I wonder if that is, I suppose that wouldn't show you the page faults. That's probably the whole thing it allocated, but well, there's a lot of stuff here, and maybe some of these things are useful to you, what you're looking at.
Yeah.
And where do these come from? They probably are in the runtime package. I mean, they come from Prometheus, but Prometheus isn't making them up.
No, yeah, I get you.
So
yeah, I can look at the Prometheus exporter to find where they're getting that from the runtime.
They're from here. So
okay.
So you maybe want to look at this. Maybe this helps, but I don't know if this would. The Go runtime maybe, well, it should be oblivious to page faults. So in that sense, it probably doesn't help. But I don't know. I'll throw this in the document.
Sure. Yeah. No, that's great. I think that was the most interesting stuff that I thought was worth sharing from my week.
Yeah. That's fun. So how does it, do you expect, this was motivated by problems for self-managed. Do you also see this relate back to a problem we're having in production, or have you come across something like that?
I I don't think so. One of the questions in my mind when I got involved with that support task was why are we not seeing this on our
Yeah.
production? And I think I'm satisfied with the answer that the fact that we're running swapless systems makes the M-advise free behavior fairly similar to the M-advise don't need behavior.
Yeah. Also, I mean, do these customers have as much RAM as we have? Because we also are, I think, a bit over provisioned on RAM, which
We
is
are
good, but
yes, yeah, especially since I'm sure that they don't have as much RAM as we do, but we did see that their GitLab process, one of these customers was able to give us the you probably know this already. There's a command line utility called pmap that has like 3 different levels of verbosity. If you run a pmap - capital X, that's the maximum verbosity, which is
I don't know the details of PMAP. I think
yeah.
I'm not even sure if I know PMAP. I was looking into PSS a while back, but then I ended up looking
Right.
at the proc file system and not at PMAP. But
yes,
go
well,
on.
you'll
Yeah.
remember from the proc file system that there's for a given process ID, there's a maps file and there's an smaps file, and the smaps
Yeah.
file is much richer information,
Well, I
but it's
think
also more
smaps is
expensive.
where I found the PSS. Yeah.
Yes.
Oh, right. I
So
didn't even think about what the cost is of looking at that, because it just
right.
looks like a file, but of course it isn't.
Right. Yes. No. Exactly. I actually did some profiling work to show how expensive it is to read the smaps file for a process, because I think a lot of people were kind of thinking that it was really cheap, and it's only cheap under certain circumstances. So it's easy to kind of trick yourself into thinking it's always cheap, but it's not. In fact, the more memory that's allocated, the more expensive it is to do
Yeah.
the walk. But I digress.
Yeah.
You're familiar
Okay.
with the smaps file. PMAP
A little
is,
bit. Go ahead. Yeah.
yeah, PMAP is, you'll love it. Just try that sometime. PMAP is reading the smaps file and presenting it in a more human readable fashion.
Yeah.
It's literally just window dressing on smaps. But this customer gave us some PMAP output, and it showed that the virtual size for the GitLab process was 19.5 gigabytes, and of that, about 18 point something gigabytes was private anonymous memory, which is reasonable, but like almost 90% of that was of that private anonymous memory was in the free state, not the dirty state, which
Yeah.
means which I think means it's been released to the OS for potential reclaim, but hadn't actually been released because those pages are actually still allocated. And that's what led to the conclusion that the lazy reclaim is at fault.
Yeah. Do you know what the effect of M-advise free and M-advise don't need is on this smaps output?
That's a great question. One of the things that I wanted to do but haven't had time to do is to write a toy C program to specifically do create a map, allocate the memory, and then directly experiment.
do one or the other and look at smaps. Yeah.
Yes, exactly.
That sounds
So,
like it would. It might teach us a lot, and it's probably not that much time to do that.
Yeah. I got partway into it and then got pulled into an incident. So
right. Yeah. No, I didn't mean to suggest it's trivial. It's just like it's an experiment with a reasonable amount of effort and potentially a high reward in what you learn from it.
I think so. Yeah.
Yeah.
I haven't given up on going back to it. I've saved my partial results. I wasn't going to admit that though until you kind of pressed me.
Well, yes, I think writing C programs to try things out is good.
I think so too. Yeah. I mean, you have so much more direct control over exactly what's going on.
Sometimes you just want to know how something works, and that's the best way to find out. Yeah.
Yeah. Totally with you. Yeah. So that's that. I think that's all I had for that topic. Unless you had other questions.
No, not necessarily. It was nice to hear this first person, and because I heard I saw a recording from 1 or 2 weeks ago. So
yeah,
that was interesting. Yeah. Okay.
Oh, this is a total tangent. You mentioned at one point recently, I think this was in I forget if it was Slack or an issue, but you mentioned that that you were having oh, actually it was probably this thing that you just demoed, that you started off trying to get some perf profiles from Gitly and were being thwarted by the fact that when we do package installs, it
Yes.
clobbers the on disk binary. That is so obnoxious.
Yes.
I
Well,
have, under certain circumstances, I've been able to kind of, work around that, and other circumstances I don't have a workaround for. So
I have
sometime when you got some time, I'd love to kind of pair with you and show you what I've kind of the partial workarounds that I do have.
I guess that so from a slightly different perspective,
Yes.
I know Omnibus from way back, but way back I knew Omnibus
Okay.
very deeply.
Okay.
And I think that actually I'm not even sure this makes sense, but I think Omnibus has some things, well, it's just chef code, right? And it does things to try and not restart processes unnecessarily. So it
Yes.
could be that there's something in our Omnibus cookbooks that manage Gitly internally
Mhm.
to Omnibus, that it decides not to restart the process after the upload because it thinks it's the same, but it's not
Yes.
literally the same, and
Right.
we ought to restart it.
Yeah.
Now, there's of course a good reason for not restarting processes all the time because people know this,
Yes.
and for a long time in the early days of Gitly that was true, but uh, a couple of years into Gitly's existence, somebody, I think Alessio, sat down to do the hard work to do something where we have a file descriptor sharing, whatnot, live reload thing.
Okay.
So we
I was
actually
going to
have,
ask if
yeah,
you knew how that worked.
we have
This.
Gitly live reload. So if we
Okay.
just change Omnibus so that it always restarts Gitly, if I don't know what the criterion is right now, but it might be too lax. And if we make it more strict so that it does more restarts, it should not impact users. And then the problem goes away because the running
Yeah.
binary is the deployed binary.
Yes.
Uh, hopefully that's possible. I haven't sat down and looked into if that's actually what's going on. One
Okay.
thing about that I wanted to say
Yeah.
is that I ended up working around that because I wanted more Go runtime profile information. And I
Yeah.
sometimes look at the continuous profiler, which is really nice, but
Yeah.
it doesn't tell you what host you're looking at. And
Yes.
we have, or I've been focusing on problems that are local to specific hosts.
Yes.
So I ended up just, and I really like the, well, from what you can tell, I like the heap allocations profile.
Sure. Yeah.
so,
Yeah.
uh, so I ended up writing a little script that just SSHs to a machine and grabs those profiles anyway.
Mhm.
So, and
Yeah.
then I don't care that the binary doesn't match because Go, these binaries are fairly big because Go puts enough information in there that it can
Mhm.
generate a self-contained profile.
Mhm.
So once you download a profile that way, you don't need to know what's running or anything.
Yeah.
But it would be, it's so much nicer when you can see in perf what's going on.
Mhm.
That was really nice. Yeah, and because I did my experiments on a test VM that doesn't get deployed all the time, I knew that the
Yes.
running binary matched what's on disk, so the perf things had a
Yes.
nice full picture. Yeah,
Yes. There's a yeah, perf is one of those multi-tools where it has so much functionality that I don't think any human being uses all of it.
I really only use the CPU graphs. I get
Yeah,
so
yeah,
much
yeah.
mileage out of those that
Yes.
I don't need to look at. I find something there and then I start looking and I don't need to come back.
Yeah. Perf has kind of two with regard to like doing profiling. Perf's got kind of two modes of operation, and most of the time I use the timer based frequency sampling, um, which I think that's what most folks use it for.
Yeah,
But you can also say I want to instrument a particular function and capture every call to that function. So that
that
second
is
mode,
risky because if that function gets called a lot, you
yes,
have a lot of
exactly,
overheads. Yeah,
exactly, and that's why I always run perf stat on that function for a few seconds to kind of get a count of how often it gets called before doing
yeah.
anything more expensive. Um, and on the occasions when you want to instrument a function that does get called kind of often enough that you're worried about the overhead, there's support for sampling 1 out of every n occurrences.
That's what you did on that. Well, that wasn't a function call, but that was a that page fault thing. You also did subsampling.
Exactly. So I was actually in the act of trying to do that. I discovered kind of a gotcha that I was really surprised at. The interface for specifying that you want 1 out of every n events just silently didn't work for the first 2 attempts I made. There are several perf events that you can use for trying to catch page faults, and the ones I started with were kprobe events and trace points. And for both of those, it silently ignores any specification about only get 1 out of every n events.
So you got all of them anyway.
Got all of them, yes. And it was like, a few hundred megabytes worth of perf data, and no doubt slowed the system down for the 30 seconds I was doing the profile, which it isn't a huge deal, but it's not what I wanted. So, so because the tool didn't work the way I wanted, I did some digging into it. It turns out that only certain kinds of there are a few types of perf events, and only certain types of perf events appear to support that. And as far as I can tell, this is not documented behavior. So
yeah, I found it very. I tried reading about this stuff in that Brendan Gregg book about eBPF, and I just get lost in all the different kinds of profiles you have. And in the end, I realized I really like flame graphs. I think he invented them, or he sort of championed them anyway. So I also don't want to make these mistakes you just described, so that's why I just stay away. And the CPU sampling, like the frequency sampling.
Yeah, and that's sufficient for most cases. So but I think this is the first time that I needed to that I felt like I needed to actually instrument a high frequency function call. And I did work out a way to do it. I found out that the software type of perf events does support this, and the kprobe and trace point events do not, at least as of our current version of perf.
Yeah, there was something. I guess perf at one point, or parts of perf are probably using eBPF by now anyway internally.
And that's going to increase over time. There's talking about BPF. I mean, I feel like we're kind of in an era of just massively improved observability for systems, and I'm so happy to get to explore this. Like what we were just talking about a few minutes ago. I think probably the right approach there I think a reasonable approach there is to write a BPF program that instruments entry into the frame before doing the page fault, as well as the page fault events, and only emit events, whether it's a counter or a stack trace, where the flag's been set by the earlier frame. And that should be a lot cheaper than saying for every one of the high frequency events, the page faults, examine the stack.
Right. Yeah, that's the wrong way around.
Massively cheaper. Exactly. And BPF's a perfect tool for doing that. It's kind of obnoxious to do it. Like there are kind of 2 interfaces for working with BPF, and there's the BCC suite, the BPF compiler collection. And I got about a year and a half ago, I got that installed on all of our servers. But the other interface is BPF Trace, which is
BPF Trace, right? Yeah, that's because they're basically recreating dtrace, but for BPF. Yeah, exactly.
And it's unfortunately difficult to get that working on the version of Ubuntu that we have installed on most of our fleet. So once we get upgraded past a certain point, it'll become trivial to install that. But I really, really, really wanted that to be on all of our boxes too, but I just didn't have the time to, because we have to compile it from source. And
it's funny, we're just waiting for Linux to catch up with Solaris enough to get some of their goodies.
Many, many years ago, I introduced Solaris boxes at the company I was working for at the time for 2 reasons. One was dtrace.
I've seen people say so often. Yeah, I've heard. the people who use it are so who got to use it were so enthusiastic about it that yeah, it's really nice that I guess enough of these people, like Oracle did everybody a favor by buying Sun and killing Solaris,
Yes.
because a bunch of these people left and ended up in
Yes.
Linux shops, and they ended up recreating the good bits. And
Yes. Yes. Yeah, prior to that, the best thing we had going on the Linux side was System Tap, and it was just, I mean, it really tried. But it had some kind of critical failure flaws. Like it was one of the things that BPF programs tend to do really well is avoid locking across CPUs, and it was really easy to write a System Tap instrumentation that had a global data structure, and that means the more CPUs you got, the more cross CPU locking you've got, and it ends up introducing an enormous bottleneck in the system that you're trying to profile. BPF
yeah,
just
which is not what you
generally
want.
doesn't do that. Yeah.
Yeah. Yeah. So just wait for the next Ubuntu.
Yep. Sounds like it. I feel like more people will be comfortable using, kind of using BPF to explore a system once we get BPF trace available. And I think that's really important for like, career development and just, learning more about the systems that we operate. But for now, what we've got is the BPF BCC suites and perf. So.
Yeah, something I've been wondering is if there's a sane way to make these just these very basic frequency CPU per flame graphs more accessible, because in a way I asked for production access just to get those things, and
Yes.
I'm getting a lot of mileage out of them, but I'm sure other
Yes.
people would too, and we can't give all of them production access.
Yes, I agree. Jakob, I think it was you that actually asked for this several months ago, to have object, just do uploads
Yeah.
of perf scripts to object storage for Giddily nodes. We can totally do that. We just need to. I mean,
yeah.
There's no technical obstacle to doing
No,
that.
I think I think there's also just more of a social obstacle, is that the people who need this maybe don't know that this exists. So we also need to find the people, because I know I need this, but I have production access, so I'm fine.
Yes.
But there are people who, if they had this, could do interesting things or have interesting insights.
Yeah.
But if we build this and nobody looks at it, then it's a waste of time.
Yeah. I agree.
So we also need an audience.
Yeah,
and
this is part of why I try to share flame graphs, like the SVG files, as well as like static images with like circled and annotated text on it, just to kind of make it more accessible and kind of show people how to interpret it. I think it's so empowering, and I really want people to have
it really has been for me, because this whole Pack Objects Cache project started because there was a flame graph of an incident in December, and I got to download it and be like, wait, what's going on here? And I finally yeah, I mean, they're weird because they don't always tell you the whole story, or it's not always clear what conclusions you can draw from a flame graph.
Yeah,
but you can see so much more than you can with a lot of more basic tools.
Totally agree. And there's like, I mean, most of the time we're talking about CPU profiling, but of course it's, flame graph is just a format, a format for representing, abstract data. So like there are other kinds of events that are sometimes applicable to, like
the heap allocations or
heap allocations,
or there's anything with stack traces. I guess it's a stack trace visualization if you think about it.
I feel like I'm going to go with yes on that. I've seen one or two places where people used it for things other than revealing stack dominance, but I feel like that was really abusing the format. Although it was also hilarious and useful, it's just not what you expect to see. So I'm not casting blame. I thought it was, wow, that is so weird and creative, and I don't want to do that again. Anyway. But no, I totally agree. It's really empowering to have access to that stuff, and I want more folks to have it. I've had for folks that do have production access, I think a lot of those folks are not really comfortable with it because the invocations can be kind of arcane, and you don't really know, what's safe and what's not in terms of adding overhead. So, kind of to relax that sense of anxiety, I've got a handful of, I think, three or so shell scripts that take like no arguments or one arguments.
That's what I made. So it takes one argument, which is a host.
Yeah.
And it SSHs, and it is a record with a sleep per script gzip, and then it remembers the name based on the host name and a date.
Yep.
And I have a companion script that.
The only thing I'd add to that would be for perf script, add a -- header so that you get the metadata for the host that it ran on.
Right. I sort of get that from the host name as well, but does it end up in the flame graph if you do that?
No, it's the first 20 lines or so of the
I noticed that metadata in the header, but I'm not really sure when you. So okay, the only way I consume these things is by making a flame graph, which I do offline, because it doesn't make sense to me to copy flame graph, like copy Stack Collapse perf PL onto the server, or
we actually got those installed in the default path, so you can just call stack collapse -perf.pl and flamegraph.pl
right
on the servers now.
There's not usually there's no need to do that, right? It doesn't need access to the
totally
server itself.
Yeah, absolutely do not have to do that on the servers. The
Yeah.
perf record and perf script are the only things that have to run on the servers. Yeah.
So this thing, I mean, it has this option to filter out swapper, but I usually want to see swapper anyway. But yeah, it takes the GC file from the first time and it appends .svg at the end, and then that's the output. So with those two things, I can capture my profiles, and because they're shell scripts, I can't do anything wrong. It's kind of
exactly.
Yeah,
exactly. Yeah. Yep. And that's exactly the kind of thing that I figured would make it a little bit easier for folks that do have production access to be comfortable capturing a profile. And so I make opinionated decisions about the capturing frequency and the duration of the capture and things like that. Yeah.
And the header, if you think the header needs to be in there, then the header, you can put it in there.
I like having the header because it doesn't impede the generation of the flame graph, and it does give you it tells you the exact invocation, and it gives you like some bits of metadata about what exact kernel was running and the topology of memory if you ask for that.
It doesn't
usually
hurt. I
things
agree.
Don't need, but occasionally it's helpful. Yeah.
Yeah.
I figure it's cheap. It doesn't get in the way, and on rare occasion it's helpful. So I kind of include it by habit.
So you and I write shell scripts on our computers, and we're happy. But how do you make that into something everybody can use?
I was going to put it in the chef recipe. It's one of those things that's been on the back burner for a while. I've already got the scripts. I just haven't committed them and pushed them.
So, but if you put them in chef, was your idea that they get installed on all servers?
Yeah.
So one thing I like about my script is that it also takes
the same chef recipe that installs perf.
Right.
Would also install the scripts.
But part of the problem is getting the perf profile off the server, because then you need to run SCP or something to get the file off. And what I like about my script is that it just uses, well, not literally SCP, but the data ends up on my computer, which is where I want it, and not in my home directory on what server was I on 5 minutes ago. So for me, an ideal solution would be something that people run locally, or it would be a web interface where you just click and it downloads to your download folder.
Sure. Yeah, I think that's very reasonable.
But I haven't found, I haven't thought about it too much, but like if there's some sort of way to get this right with a reasonable amount of effort, it would be very nice. But yeah, still not sure.
Yeah, that's. I agree. That would be nice. I was looking for something low cost that was likely to get done quickly, and even just deploying those shell scripts, I haven't done. I don't have a good excuse for that. It's just
and you do chef all day, or well, not all day, but you regularly do that sort of stuff. I don't even do that sort of stuff.
Yeah. Just like I've got a set of tutorials that I've got half written for kind of teaching people how to read flame graphs and how to use perf and BPF tools, and it takes time. All this stuff takes time, and there's so many other options.
is it normal for people for people with production access to have to run books on their computer?
It's normal. Yeah, I'd
Yeah.
say so.
So if I put my scripts in the run books, then everybody would have them on their computer.
I guess so.
So maybe that's the solution for my approach to the problem. Maybe I should just submit a
Sure.
runbooks merge request.
I don't think that would be a problem.
Yeah. Now people need to know they're there, but that takes care of installing the script because it's just git pull. Well, okay. We've been talking for more than an hour. I think we should.
Yeah.
We should wrap it up. Thanks for the demo meeting.
Thank you for the demo. Yeah,
Yeah.
no, this was great.
Thank you too, and have a great rest of your day.
Awesome. Yeah, great talking to you.
Likewise. Bye.
Bye.